All right. Yeah, so let's just get started. My name is Josh Farina from Pensacola, Florida. I work by HMC. I'm one of the mechanical guys on the Nadia project, building humanoid robots. I think there's nothing cooler. So we decided to make humanoid robots way more complicated by using really complicated carbon fiber parts. And these make up most of the structure of the robot, including the legs and actually the arms, kind of connecting the motors together and housing the actuators, and also for the torso. So why carbon fiber? I decided to ask ChatGPT, why not? And really kind of gave me an answer that makes sense, right? Lighter weight, you want a high strength to weight ratio, it can really be to a carbon fiber. You get flexibility in the design of the actual parts, because these surfaces, you can kind of mold them over, make really pretty legs. It actually protects from some impacts. However, carbon fiber isn't very hard. So yeah, you have to kind of consider it when it's like smashing into stuff, which it does a lot. So the main things we're going to be looking at in this presentation are the torso, the foot plate, and the thigh shell. So just to kind of start, how are we actually making these parts? We start with an internal mold, and they're collapsible. And we try to design the mold to focus on what other parts are actually mating to these carbon fiber parts, and we're trying to control those surfaces. So we start by doing that by using this internal mold that is made of these precision machine parts, and they kind of assemble together, and then all these shafts and screws kind of position where I actually need the most high tolerance for mating parts. And then the molds are collapsible and removable, so we kind of have to design our parts so we can actually take the mold out once they're made, or you'll make a big block of garbage. So really, we actually use 3D printed for these molds, and really the only thing you have to consider is the thermal expansion when it comes to tolerancing the parts, but it's pretty insignificant, so we just kind of ignore it. When now it comes to making the part, we kind of start with this pre-preg. If you're not familiar, it's just the actual weave already impregnated with the epoxy. And it's pretty nice because you just cut out the shapes. We template it out so the layers actually don't have any discontinuities. So you can kind of build up the thickness to what you need. In this actual example, we assemble the mold first. We have all these screws that actually are tolerance to mate to the other parts. We layer by layer. We put it in this vacuum bag that squeezes it for 14 hours. And then we post-process it. We remove the burrs, and then we get this pretty part. So there is kind of a couple issues with doing it this way, using only plain weave. If you're not familiar, it's the one that goes crisscross underneath each other. Layers tend to shift and they kind of fall over each other, which is not really ideal because you get these stress concentrations. You want those fibers to be straight to take that load. And then areas where thickness is important, the way you're actually vacuum bagging this and a couple other ways, just kind of how we're compromising in our design. You get variability between parts, and it's really frustrating. Also, if you assume isotropic behavior for this, you're kind of in the wrong ballpark because you're not really utilizing the fiber's tensile strength, right, where you need it in the structure. So actually, when you actually start looking at these load paths and these stress analysis for deformations, very little of the final part weight is contributing to the actual structural performance. So what do we actually do? It's pretty simple. You just take this unidirectional carbon fiber and add it where you need it. And just the case study we're going to look at is the thigh shell. And the way we kind of are how do we actually get our requirements for our robot is we look at the joint stiffness, and this is really determined from the actual external forces, right? We have actual forces on the ground in different directions, and also seen by the transmission, right? Because the actuators inside these thighs are actually attached to the structure, because that carbon shells are actually the structure of the robot, and kind of we want that deflection to be within, a small error for the leg, right? We don't really want that estimation to be off. So to kind of simplify our loading conditions, we're all right, put a torque about each axis on pitch, roll, and yaw, and then we're going to compare our FEA and our real-life testing with our prototype to kind of get an estimation of, all right, are we going in the right direction for reinforcing our parts? So we kind of have all these strategies for how do we actually put these unidirectional in the actual structure, and we have a bunch of these, and we just put them all in a bunch of combinations, and we make this really freaking long tree and ANSYS, which is pretty nice because you can kind of multi-thread and go through all these different combinations. The issue is how the heck do you interpret that data? Bear with me here. We kind of look at two different things. It's the deviation from that deformation percentage which is just looking at all those loading conditions that are actually in the structure of the part. You don't really want them to be different when it comes to like loading the leg, because you get different kind of strain rates and stuff within the carbon fiber. So the idea is the deviation from that average, you kind of want it to be minimal. And then when we actually load on the mount in the shaft or like internal parts, we want it to be pretty similar. So on the left, you kind of see what strategy we chose, and the basic rule of thumb is just kind of connecting where this actual connects to the part. And on the right is the lumpy part at the end. That kind of does its job. We actually reduced the mass by quite a bit. Each thigh is only around 800 grams. We use half the amount of plain weave layers, and we actually increase the joint stiffness. So where else can we use this? We use it in a foot here, but in this case we use it in a compression mold where we take the bottom and the top of the mold, we put down the plain weave, and then we actually add unidirectional reinforcement along these ribs. So way over-engineered, but it works. So it's actually cool if you, along the neutral axis of the foot, if you put chop fiber, you can decouple the strain rates of the unidirectional and the plain weave, so you don't get these like interlaminar shear where you actually have the part actually failing. I actually have another part if you want to see it like a cutaway. You can see kind of how there's no voids that are created, which is kind of cool. Does it work? It defeats your German engineering. It survives it. Yeah, that's really all I got for you guys, but thank you. I also have the part here if you want to see it. Check it out. Questions?
Can you expand on the chopped fiber addition? That sounded important, but
yeah, I kind of glanced over that a little bit. It's really just taking the fibers and chopping them up, and then you put them in like an epoxy, and you're kind of, it's a little more moldable since those fibers can move around in the epoxy, and it's just meant to take the gap between, when you actually squish it together. Lamborghini actually developed this, and they actually made a whole chassis to their car. And when you actually press it all together, you get comparable results to like a softer aluminum, like a 6061, but it's nowhere near as strong. It's just like a continuous fiber.
And are you putting it between the layers, or just
yeah,
the gaps?
So you have the weave in the bottom, weave on the top, and you have unidirectional, and then when you squeeze both together, you might have gaps. So it's really just kind of putting it in there, filling it in, squeezing it, and then you have excess that comes out.
How do you make that internal mold collapsible without skeleton structure?
Yeah, it sucks. It's really, you're kind of designing the part. I would use the same principle as like injection molding, where you have that drafting where you want to be able to remove it. But you kind of just design your structure since it's 3D printed. You can kind of mess up a couple times if you need to, but you want to undo the structure first, and then you can kind of collapse it in order in the back. The only problem with that is if somehow the resin gets into the mold and then it all bonds together and it's all serial on how you take it apart, you just made a block of garbage. Yeah. So you have to kind of think about that a little bit.
This is really cool. So I just have a quick question about kind of the accuracy of your FEA models versus what you guys are seeing. So with hand-laid carbon fiber, at least in my experience, it's extremely hard to get consistency across different parts and replication. So can you touch on if you feel like you're getting consistent mechanical results if you duplicate the same design, and then is your FEA kind of hitting the mid-level between any sort of variability you're seeing with mechanical
Yeah,
parts?
that's a super good question, and that is like the vein of doing any type of composites. When we were actually testing them, I didn't touch on this point, but we were seeing about 9% offset consistently through our FEA results and our real-life testing. So we just scaled that, and we got pretty small percentage deviation. I don't know where that came from. Maybe it's our experience with FEA. But between parts, we made a left thigh and a right thigh using these reinforcement method, and consistently we were in 5% of like our deviation. To be fair, I mean, we are making it by hand, but yeah.
About the validation for the flexibility of the final part, you had this picture, I think the previous slide, with the leg horizontal and with this one. So here you are only measuring the statically, or you are adding also weight. I know it's also weight.
Yeah. It's really just, you're kind of, the issue is how the heck do you measure it?
Yeah.
And it's just like, what actually doesn't change and what has a consistent profile. We're just using dial indicators, and you're just loading it, just trying to keep it simple. But we're just kind of turning the leg according to like what actual axis we're at, we want to evaluate, and just measuring the deflection totally over the leg. And it kind of figures off.
And what's the, let's say, the acceptable flexibility that you have on the overall structure here?
Like magnitude of deflection, actually around 2 millimeters.
So 2 millimeters is already good.
It's pretty good, it's pretty
Yeah.
safe. And that's the benefit of using, carbon fiber.
Yeah.